welcome to the new session of COALP. In last lecture, we have covered various shifts. Today, our topic of discussion will be ALSU, which stands for Arithmetic Logic Shift Unit, right? So instead of having individual registers performing the micro operations directly, computer systems employ a number of storage registers connected to a common operational unit called a arithmetic logic unit, abbreviated as ALSU. To perform a micro operation, the contents of specified registers are placed in the inputs of the common ALSU. So let me show you the diagram first. So here you can see the upper one is the diagram for ALSU, Arithmetic Logic Shift Unit, right? So here we have AI and BI are the inputs. S0, S1, S2 and S3 are the control inputs, right? CI is for carry in and CI plus 1 is for next circuit. So I am showing you the one typical stage. That is why I have written I over here, right? So CI plus 1, DI, AI, BI. What does I means? I have shown you one typical stage of this circuit, although we have n number of circuits which have been attached if your ALSU is of n bits, right? So here the ALSU performs an operation and the result of the operation is then transferred to a destination register. The arithmetic logic shift unit consists of arithmetic circuit, logic circuit and shift circuit. So here you can see that this combinational circuit is composed of three things. The one is called arithmetic circuit, the another one is called logic circuit, and the third one is called shift circuit. So a total number of 14 operations have been performed using this ALSU. The arithmetic logic shift unit consists of arithmetic circuit, logic circuit and shift circuit. The circuits are combined with common selection variables which are called control inputs, right? Written with S0, S1, S2 and S3. So these are the selection inputs or control inputs. So the inputs AI and BI are applied to both the arithmetic and logic unit. So here you can see that the AI input and the BI input is connected to both the circuits. That is, it is connected with the logic circuit with the help of these two lines, and it will be connected to the arithmetic circuit with the help of these two lines, right? So this S0 and S1 have been fed into logic circuit and to arithmetic circuit, right? Because S0 and S1 is basically used to select the particular micro operation, S0 and S1. Similarly, S2 and S3 is basically used to select the data in the multiplexers. So that is why S2 and S3 is connected to the MUX. MUX stands for multiplexer, which means that it is taking multiple inputs and giving you one output, right? So multiple inputs are there and giving you one output. So here I have used 4 into 1 MUX. 1, 2, 3, 4. These are the 4 inputs which have been given to the MUX, and these are 2 control inputs, or you can say that selection lines, right? And it will give you the output in the form of F5. We'll show you its functioning in few minutes. So the inputs AI and BI are applied to both circuit, arithmetic and logic circuit. The particular micro operation is selected with the help of S1 and S node. A 4:1 multiplexer at the outputs chooses between an arithmetic output in DI. So here you can see that this is your DI, which is the output of arithmetic circuit, and between EI, which is the output of logic circuit, and a logic output in EI. The data in the multiplexer are selected with the input S3 and S2. The other two data inputs to the multiplexer receives the input AI minus 1 for the shift right operation and AI plus 1 for the shift left operation. So, right. So here AI and BI are the two inputs, or you can say that these are the two registers in which we are going to perform any operation, right? So after that, the value of S naught, I have told you this circuit will perform a total number of 14 micro operations. This circuit will perform a total number of 14 micro operations. Out of these 14 micro operations, 8 will be your arithmetic. 8 micro operations belong to the category of arithmetic. 4 micro operations belong to the category of logic micro operation, and 2 micro operations belong to the category of shift. Right? So how it will be achieved? So when the value of S1 and S node, it will be 0 0 throughout. For S node, S1 will be 0 0 throughout for 8 micro operations.
सर विजुअल नहीं है.
क्लियर है?
Yes sir.
So here we have S node S1 S node is equals to 0 0. S1 S node is equals to 0 0. Right? So for logic micro operation, S1 and S node is equals to 0 1. That is, you have a 4 combinations of this, which is equivalent to 0 1. Right? Just wait. So this is S3 and S2 instead of this. Yes, these are S3, S2, S3, S2, S3, S2 is 1 0 for right shift, and S3, S2 is equals to 1 1 for left shift. So here, this circuit will give you a total number of 14 micro operations. 8 for arithmetic, 4 for logic, and 2 for shift micro operation. Right? So each operation will be executed with the help of a total number of 5 inputs. So what are those 5 inputs? S3, S2, S1, S0, and CI. Or you can say that Cin. Cin is basically used for arithmetic shift. Cin means carry input. Because you know a carry will be generated in the form of arithmetic operations. Right? So let me show you the slide again. So here you can see that the value of the first 8 operations 1, 2, 3, 4, 5, 6, 7, 8. Transfer A to transfer A. These 8 operations are arithmetic operations, and you can see that the value of S3 and S2 is written as 0, 0, 0, 0. First 8 values are zeros, right? I hope the concept is clear. After that, for next 4 operations, and, or, XOR, complement A, these are your logic micro operations, and the value of S3 and S2 is 0, 1, 0, 1, 0, 1, 0, 1. It is fixed, right? And next we have for arithmetic shift right, SHRA, the value will be 1, 0, and it is 1, 1. Then how you are going to perform 8 operations? How you can write 8 2 raised to power 3? So let me show you this concept on the board, how these 14 operations will be implemented. So first of all, we have S3, S2, S1, S node, and C in, right? For 8 operations 0, 0, 0, 0, 0, 0, you have to put 8 times 0, 0, 1, 2, 3, 4, 5, 6, 7, one more 8. So this is your arithmetic operations. For arithmetic, you will have C in. How many arithmetic operations are there? 8. 8 can be written as 2 raised to power 3, which means you have to use 3 inputs. You have to use 3 inputs for it. 8 is equals to 2 raised to power 3. So what are the various combinations? 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, then 1, 1, 0. Last but not the least will be this. So here you can see that a total number of 8 arithmetic operations will be performed with the help of this, right? After that, the 4 logical operations. For logical operations, the value will be 1, 0, 1, 0, 1, 0, 0, 1, 0, 1, 0, 1, 0, 1, right? These are your 4. Or how you can write 4? 2 raised to power 2 can be written is equals to 4. It means a total of 2 combinations will be there. A combination, 2 combinations will be there for this. And for logic operations, your carry in will be in don't care conditions. Your carry in will be in don't care conditions. So for this you have 0, 0, 0, 1, 1, 0, 1, 1. So till this point, this is your logic. This 8 operations are arithmetic operations. These 4 operations are logic operations. I hope the concept is clear. And the last but not the least, that is your arithmetic shift. So how your arithmetic shift will be performed? So for arithmetic shift, your C in shift. How many shifts are there? Left or right? So for right arithmetic shift, the value of S3 and S2 is 1, 0, 1, 1, and all these 3 are in don't care conditions. So these are 2 shifts arithmetic and left and right. So 8 plus 4 plus 2, a total number of 14 micro operations will be performed with the help of ALSU. So I am showing you the table again. So this is your table. So first 8 values for S3 and S2 are 0, 0, 0, 0, first 8 values, right? And you will have 3 control variables. A total number of 8 combinations will be there from 000 to 111, and C in will be in don't care conditions for the remaining logical micro operations and shift micro operations, right? So a total number of 14 micro operations will be performed with the help of this one typical stage. So the output carry Ci plus 1 of a given arithmetic stage must be connected to the input carry C1 of the next stage in sequence. The circuit provides 8 arithmetic operations, 4 logic operations, and 2 shift operations. So arithmetic operations are selected with S3, S2 is equal to 0, 0. Logic operations are selected with S3, S2 is equal to 0, 1. And shift micro operations are selected with S3, S2, 1, 0 for right shift and 1, 1 for left shift. Right shift 1, 0 and 1, 1 for left shift. So next concept is, the topic is bus and memory transfer. Bus and memory transfer. So after going through this topic, you should be able to learn about the difference between bus and memory transfer. You should be able to understand the implementation of bus lines using MUX and 3-state bus buffers, or you can say that 3 bus buffers. So first of all, what is a bus? Why we use the concept of bus? Bus is a path, or you can say that a group of wires over which information is transferred from any of the several sources to any of the several destinations. Or in simple words, you can say that bus is used to transfer the information, or it is used to transfer the data between multiple registers. So in first diagram, you can see that we have registers A, register B, register C, and register D. So how, first of all, you need to put some data onto the bus from the register. After that, the data has been read from the bus by the various registers too, right? So the first diagram will show you the concept of the data has been read from the register to bus, right? And the next diagram is showing you the concept of the how the data from the bus is read to the destination register, right? So in second diagram, we have a decoder, that is 2 into 4 decoder. First of all, so these are your 4 registers, register A, B, C, and D. So suppose this is your bus. So I hope you have seen this bus. This is IDE bus or your SATA bus. SATA bus is basically used in your system these days. So only one register will put the data onto the bus lines, one at a time, right? So now how you can read this data into the registers. So for example, here some registers are connected, written with R0, R1, R2 and R3. So one decoder has been attached with the help of which we can transfer the data D0, D1, D2 and D3, right? And select, we have two selection lines Z and W. Z, W. So let me show you the board. So here you can see that. So we have four registers A, B, C, D, right? So suppose the register consists of 4 bits each. 4 bit, 4 bit, 4 bit, and 4 bit. So this is your bus which is used to transfer the data from one register to another register. So one register is putting up the data, that is the upper registers are writing the data onto the bus and the below registers are reading the data from to the bus, right? So how this writing will be performed using decoder. So here first of all E will be used to enable the decoder. So here I have used 2 into 4, which means that we have Z, W, so 0, 0, 0, 1, 1, 0, 1, 1. So these are your if the value of Z and W is 0, 0, 0, 0, decimal equivalent is 0. The decimal equivalent of 0, 0, 8, 0, which signal will be activated D node. That is R node will get the data. If you are passing 0, 0 over here, if you are passing 0, 1, the decimal value is 1, D1. D1 will be activated and with the D1, R1 register is attached. Similarly, this is for 1, 0, the value, decimal value is 2 and 1, 1, the decimal value is 3. So D2 and D3 will be activated. This is according to 8421 rule. So 0, 0 means 0, 0, 1 means 1, 1, 0 means 2 and 1, 1 means 3. So this is the decimal equivalent, right? So if I am passing 1, 1 over here, 1, 1 over here, by enabling E is equals to 1, your D3 will be activated. It means from the bus, R3 is reading the data. I hope the concept is clear. So ways of implementing bus lines. How the concept of bus is achieved We have two different methods. The first method is called with the help of multiplexer, and the second method is called three-stage bus buffers. So this is the diagram for MUX, multiplexers. So register A, register B, register C, register D. So all register is of 4 bits each. So to reduce the complexity, I have attached only the zeroth one complete value, that is A3, B3, C3 and D3. I have reduced the complexity. How? By attaching only the third input to the muxes, right? Otherwise, your diagram will be complicated. Although this A node is connected to this, A1 is connected to this, A2 is connected to this, right? And A3 I have already attached with this. I hope the concept is clear. So this is your S1 and S2, two selection lines are there, right? Which means that, so here I have used the concept of 4-line common bus because 4 inputs I am getting from the muxes, 4 into 1. 4 into 1 means the multiplexer is getting 4 inputs and it is giving you 1 as a output. And all these selection lines have been fed to each mux. How it will work? How this will work? We have two control lines, that is S node and S1. S1, S node. So here 0, 0, 0, 1, 1, 0, 1, 1. Right? So register selected. If the value of S1, S2 is 0 to all the muxes, your register A will be selected. Right? Your register, which means that A note, if the value is 0, this is your 0, this is your 0, 0 and 0. So from 0 input, all the A's, you are getting the register A value. A note to this 0, A1 to this 0, A2 to this 0 and A3 to this 0. If the value of S1 and S2 is 0, 1, your B register will be activated, which means that here you can see that along with 1, B note, B1, B2 and B3. This is your B3. Similarly for 1, 0, C register will send the data onto the bus, and for 1, 1 register B will send the data onto the bus. Right? So now the data have been placed onto this 4-line common bus. Right? So this is the concept of multiplexer. Next, the same concept will be used by second method. It will be achieved with the help of second method, and the name of the method is 3-state bus buffers. So 3-state bus buffer is a special circuit which is having one normal input A and one control input C, and you will get the output Y is equals to A as such if C is equals to 1, right? And if the value of C is equals to 0, your circuit will be in high impedance state. Your circuit will be in high impedance state. So this is your 3-state bus buffer. So this is your A simple input and this is your control input C, right? And you will get the output Y is equals to A if C is equals to 1. You will get the same output in Y as of A. For example, in A we have 101. You will get 101 in Y if C is equals to 1, and if C is equals to 0, your circuit will be in high impedance state. Your circuit will be in open state, right? So here you can see the blow diagram, bus line with 3-state bus buffers. So this is the simple stage for it. So if you have 4 bits of registers, you have 4 circuits of this similar type, right? If you have to put 4 bits of data onto the bus line, so this single circuit represents 1 bit, right? So similarly, you have one more circuit for A1, B1, C1, D1, one more circuit for A2, B2, C2, D2, and one more circuit for A3, B3, C3, and D3. I hope the concept is clear to you. So this is the second method for the implementation of 3-state bus buffer. So with the help of RTL, how you can write this concept? So depending on whether the bus is to be mentioned explicitly or not, register transfer can be indicated as either. So R1, if you have to perform the transfer between R1 to R2, so first of all, you have to put the data from R1 register onto the bus, and then you are going to read the data from the bus, right? I hope the concept is clear. First of all, you need to put the data from the register onto the bus, and then you are going to read the data from the bus to the R2 register. So this is one is the RTL. So the next concept is memory transfer. In previous slides, we have just covered bus transfer. The next concept is memory transfer. So memory or RAM can be thought as a sequential circuit containing some number of registers. These registers hold the words of memory. Each of the registers is indicated by an address. These addresses range from 0 to R-1. Each register can hold n bits of data. Assume the RAM contains R is equals to 2k words. It needs the following, right? If your RAM contains R is equals to 2k words, then it needs the following lines. The first of all, n data input lines. Input should be there, so that is represented with n number of lines. N data output lines. If n input data lines are there, there has to be some data output lines. Then address lines. So here we have used k address lines. And a read signal is there and a write signal is there. So memory transfer. So collectively, the memory is viewed at the register level as a device, and it will be denoted with the help of capital M. So memory is usually accessed in computer systems by putting the desired address in a special register called memory address register, MAR, or simply AR. Remember this definition. A special register which deals with addresses, it is called MAR, memory address register, MAR, or simply AR. So basically a read operation says that the transfer of information from a memory word to outside world. This is called memory read operation, right? A transfer of information from the memory to outside world. This is called memory read operation. And the transfer of new information to be stored, a transfer of new information to be stored into the memory is called write operation. So when the memory is accessed, the contents of MAR get sent to the memory units address lines, right? Whether you are performing read operation or you are going for write operation, in both the cases, you need a memory location. For example, we have 49 students, right? If I have to visit Mohit Kumar, right? If I have to visit Mohit Kumar's home, I should know the address of Mohit Kumar. Similarly, if you have to read some word, from the memory, you should know the location, right? So that location will be present in address register. So this is your read, write, data out, data in. So when you are sending data from the memory to the outside environment, this is called, then read operation will be executed, right? So suppose this is your data register. You are sending data from the memory using data output lines to the data register. This is called read operation. And when you are sending something, when you are writing something onto the memory location, you are putting something, you are storing something onto this, and that operation is called read operation. I hope the concept is clear to all of you. Memory read and memory write. So this is the memory read operation. To read a value from a location in memory and load into a register, the register transfer language notation looks like this. So memory read operation. R1 M of MAR, or it will be written as R1 M of AR. So first of all, you should know the location where to read the data from the memory, right? Once you are getting the memory location in AR, after that, the read signal will be activated. The value of read is equals to 1, and the contents of M of AR, it will be transferred to the R1. This is called read micro operation, right? This is called read micro operation, memory read operation. First of all, once you should know the location where the contents are stored. You should know the address of the memory. after getting the address, the value of read becomes 1 and the contents of MAR, it will be transferred to the R1 register using data output lines. Using, so this is your AR, this is your M, and this is your read operation. This is your data output lines, which is further connected to DR, or you can say in this case we have R1 is connected to R1. So this is your read operation. Similarly, you can perform the write operation. So how write operation will be performed? So you have MAR. This time you have a memory, you have address. In both the cases, you should know the location where to read the contents or where you are going to store the data. In this case, we have data in, right? And your write will be activated to 1. The value of write where your R1 is attached. So first of all, the contents of the MAR get sent to the memory address line. That is, first of all, the address will be sent to the memory. For example, 1010 is the address. So from this address, the data value is 500. The data stored at 101 location is 500. After that, the write signal becomes activated and the contents, that is your 500, will be stored, will be saved. So first of all, because I am using write operation and R1 is having 100 value and 1010 is having 500 value. Let me show you the live example. R1 is having 100 value. So first of all, you should know the address. At 1010, the data value is 500. So after the write operation, the 100 value will be overwritten and the new value at 1010 will be 100. So this is your write operation. So this is your write operation. So summary of register transfer micro operations. So in the first case, that contents of register B will be sent to register A. In second case, the contents of AD portion of the data register will be sent to address register. In third case, the constant value will be transferred to A register. In fourth case, we have two operations which is written with the help of comma. The contents of R1 will be written onto the data bus, address bus, and from address bus, it will be sent to R2. AR stands for address register, DR stands for data register, right? MR means memory word specified by register R. And simple M denotes M of AR. Where M goes to DR means a read operation and DR goes to M means a write operation. So let's do some numerical. So the first numerical is an 8-bit register contains the binary value. An 8-bit register contains the binary value 100111100 full stop. What is the register value after an ASHR? ASHR, you have to perform arithmetic shift right operation, and starting from the initial number, that is the same number, determine the register value after an ASHL, right? Again, you need to perform 100111100 ASHL and state whether there is an overflow or not, right? So first of all, we need to perform the arithmetic shift right operation on the value ASHR. As you know, arithmetic shift right, what it is doing, what it will do. The first bit is your sign bit. It will rotate that bit to first position and one next position for next bit. It will move the first bit to the first position and the first bit to the next location. So after the ASHR, the value becomes 1 1 0 0 1 1 1 0, and the last will be 0 will be discarded. I hope the concept is clear to you. I'm repeating you again. In arithmetic shift right operation, the sign bit will be taking the first position and it will be moved to the second position, and all the remaining bits are moving to the next position, one position to the next, and your last 0 will be discarded. So this will be your answer after our ASHR. So second portion says that what will be the value after ASHL and state whether there is an overflow or not. So in case of ASHL, a 0 will be inserted. This is your sign bit. A 0 will be inserted from the right hand side and all the remaining bits will be moved to the left position. So your answer will become 0 0 0 1 1 1 0 0, and this one will be discarded. So here you can see that there is a change of bit. First of all, you have 1 and now you have 0. It means a sign reversal occurs. If there is a sign reversal, it means that there is an overflow. How we have checked the concept of overflow? With the help of XOR gate, right? If you remember the concept, so this is your register which is of 8 bits. So this is the original value. That is 1 0 0 1 1 1 0 0. So we are attaching the XOR gate to the last 2 bits. So this is your sign bit. If the value of V is equals to 1, if the value of V is equals to 1, there is a concept of overflow. Here you can see that 1 0. In case of XOR gate, 0 0 0 1 1 0 1 1. So here you are getting 1 and here you are getting 0. So this means V is equals to 1 1 0. V is equals to 1. So there is a sign reversal. Before the shift, you have 1 as a sign bit, and after the shift, you have a 0. It means there is an concept of overflow. So this is done for today.